All right, for our next talk, I'd like to introduce Magda Celejewski. I'm sorry if I butchered your last name, but please welcome Magda for our next presentation.
So the last name is Celejewski, so close enough. This talk is titled A Novel Method for Pore Water Characterization in Low Permeability Media. It will discuss a new method that I've developed with Tom L at the University of Ottawa. So we want to characterize the pore water composition and chemistry of low permeability rocks because pore water chemistry can provide us insight into the pore water origin, so what the foundational water within these formations is, transport mechanisms that dictate the movement of solutes throughout these formations, so whether we have advective or diffusive dominated transport, reaction processes that can occur, so mineral dissolution and precipitation reactions, as well as any ion exchange. And all of this is important to understand the residence times of solutes and fluids within the formations, which is important when developing waste storage solutions, as well as for understanding the geotechnical stability within specifically sensitive marine muds. So here is a photo of a mudslide that occurred in the Champlain Sea mud that was caused by desalinization of the pore water. There are several methods that exist for extracting and characterizing pore waters from low permeability materials. These include advective displacement, high pressure squeezing, ultracentrifugation, crush and leach, and out diffusion. All of these methods come with their own sets of limitations. Many are dependent on external porosity measurements. So a method used by the Clark Group at University of Ottawa that extracts pore waters by crush and leach uses vacuum distillation to determine the amount of pore water extracted. We're also working with very small pore water masses, which makes measurements difficult. And many of these methods are susceptible to mineral dissolution and ion exchange reactions during the extraction process. When we extract pore waters using different methods, we need to understand the system from which we're extracting pore waters from. So here is a schematic of a clay rock. We have different types of pore water within clay rocks. So mobile water, which contains both cations and anions, and is found in the larger pore spaces. This mobile water is at equilibrium with bound water, which is found on the negatively charged mineral surfaces. We have both diffuse double layer water, which is a cation-rich water directly in contact with the mobile water, and interlayer water, which is found within swelling clay minerals. The objectives of this work were to develop this new method for pore water extraction and characterization. This is the paper absorption method, which involves placing an absorbent material between two core segments, pressing the whole thing tight, and allowing water to move from the core into the paper by capillary action. And this method aims to extract that mobile water. We also want to compare the results of this new method to those of a crush and leach pore water extraction technique. The samples we worked on were obtained from the Michigan Basin shales at the Bruce nuclear site in Ontario, the opalinous clay from the Moncherie Underground Research Laboratory in Switzerland, and the Champlain Sea mud from Orleans, Ontario. All of these samples have low hydraulic conductivities, with the lowest hydraulic conductivities in the shales and the highest in the muds, and a range of porosities, with the lowest porosities in the shales, so 6 to 7% in the shales, and up to 65% porosity in the muds. The paper absorption method that I will present here is our most recent iteration of the method. This method has undergone a few iterations over its development, but this particular method has been used to report pore water concentrations. So we begin by cleaving or segmenting our cores inside of a humidity chamber. The humidity chamber works to prevent evaporation from these freshly exposed core surfaces. We insert our paper between the core segments, again inside this humidity chamber. And then we wrap the whole puck system up, isolating it from the environment and allowing our pore water to equilibrate for about 50 days, depending on the material we're extracting pore water from, at 5 degrees Celsius. After this equilibration period, the papers are removed from the cores and placed inside these FEP envelopes. Again, this is done within this humidity chamber to mitigate the effects of evaporation. The water content of the paper is then measured using near-infrared spectrometry, and then the solutes are leached from the papers and analyzed by ICP-OES and ICP-MS. And then from these separate measurements of water mass and solute mass, we can report pore water concentrations. The crush and leach method used to extract pore waters from the Michigan Basin shales and opalinaceous clays involved crushing our rocks to a 2 to 4 millimeter grain size, leaching for 24 hours using a solid to liquid ratio of 1 to 4. The Champlain Sea muds, the samples disaggregated in DI water and were agitated for 5 to 25 minutes with a solid to liquid ratio of 2 to 1. Now, looking at our results, I will focus here on chloride-bromide mass ratios, sticking to solute masses, because when extracting waters from the Michigan Basin shales and opalinaceous clays, the paper absorption method was in its early stages of development, and we could only report solute masses. Also focusing on chloride and bromide only, because chloride and bromide are considered to be conservative natural tracers, which means that the chloride-bromide ratios reported by different methods should compare well to each other. However, this is not what we see here. So the paper absorption method, depicted in blue, presents a lower chloride-bromide ratio than that of the Michigan Basin shales. So we see a discrepancy between the two methods. In the opalinaceous clay, there is a smaller discrepancy, and in the Champlain Sea muds, there is no difference. So why do we see this discrepancy? So again, we need to understand the types of pore water we're extracting. The paper absorption method aims to extract just the mobile water from the largest, most interconnected pore spaces, whereas the crush and leach method will extract both diffuse double layer water and mobile water and interlayer water. So it samples everything. So why should this make a difference to chloride-bromide mass ratios? Well, if we look at our hydrated ionic radii of bromide, we see that the bromide anion is slightly larger than the chloride anion. We know in these clay-rich sedimentary rocks, we can have anion exclusion effects, and these can be complete anion exclusion, where the diffuse double layer overlaps, preventing the movement of anions through the pore formation, so between pore spaces. We can also have size-specific anion exclusion, which occurs where the diffuse double layers come close to each other, but don't quite overlap, which means that the smaller chloride anion can move through our pore spaces, whereas the bromide anion will become fractionated in the larger, more connected pore spaces, which is the water that we extract using the paper absorption method. So if we go back to our chloride-bromide mass ratios, this is what we see. We see a size-specific anion exclusion, with our paper absorption method extracting higher amounts of bromide to chloride than the crush and leach method. The Michigan Basin shales are more susceptible to this size-specific anion exclusion because of these small pore throat diameters within these rocks. In the opalinaceous clays, we have slightly larger pore throat diameters, and we see less of a discrepancy between the two methods. And then finally, in the Champlain Sea muds, where we have relatively large pore throats, we see that the crush and leach and paper absorption methods compare very well to each other. So now hopping over to some work conducted by our colleague Carla Rose in 2021, where she used our final iteration of the paper absorption method to extract pore waters from opalinaceous clays, and was able to report pore water concentrations in these pore water extracts. The opalinaceous clay is a well-studied formation, so there is a lot of pore water data available for pore waters extracted from the sedimentary rock using many different methods. These plots here present some data plotted or extracted using both squeezing and borehole seepage collection over the years. Generally, this data is plotted as concentration from the distance of the top of the opalinaceous clay. So we have concentration on the y-axis and the distance from the top of the clay on the x-axis. And when plotting our paper absorption concentrations in this manner, comparing them to previous data sets, we see that the concentrations reported by the paper absorption method compare well to those concentrations reported by previous methods. And this is true for chloride and sodium, as well as calcium and magnesium. In potassium, there's a lot of scatter of the data, but also we have a good comparison to this other data set. Strontium and sulfate also compare well. So, to conclude, we have shown that the paper absorption method extracts the mobile water from the largest, most interconnected pore spaces while maintaining an equilibrium between the bound and mobile waters. We've also shown that the composition of the mobile pore water is different from that of the total water, which is extracted by the crush and leach method. Additionally, that the anionic composition in the mobile water is affected by pore size distribution. So we can get fractionation of larger anions in the larger pore spaces, and this is caused by size-specific anion exclusion effects. And these are much more obvious where we have small pore throat diameters. We've also applied the paper absorption method to extract solutes from these low permeability clay-rich rocks and have been able to report solute concentrations in pore water extracts or in pore waters extracted with this method to those extracted with different methods. And thanks for listening.